All right, we're continuing our video lecture series on chapter 2.6 from the Lock 5 textbook. All right, we finished the last lecture looking at a snapshot of stat key, which is what I'm going to use to show you how to get the regression line in this class, which you can use during exams, assignments, and whatnot. In general, I don't care what software you use to come up with the line of best fit, as long as you have something you're comfortable with. All right, and unlike correlation, you remember from 2.5, we said correlation is the same value no matter what variable is your explanatory and what variable is your response. But for linear regression, it definitely does matter. For example, if we take the temperature equals 37.7 plus 0.23 chirps, if we switch those two variables, the numbers change very much. And what happens here is a little algebra. If you call this y and x, and switch x and y and solve, you're going to get this value here. So you do want to be careful which is your explanatory and what is your response variable. But I'm going to go over how to upload data into StatKey and how to create a line of best fit in the last couple videos of this lesson. All right, so looking at the regression line in a little bit more detail. Here we have the slope. This is going to be the parameter, the number that goes next to your explanatory variable, x. The number all by itself is going to be the intercept, the y-axis intercept. And that slope tells us the increase in predicted y for every unit increase in x. All right, now keep in mind the slope could be negative, so this could be decrease. So I should say increase or decrease in predicted y for every unit increase in x. And the interpretation of that intercept is what's the y value when x equals 0. We'll go back, and sometimes this makes perfect sense, and sometimes it doesn't at all. So if we go back to the interpreting slope and intercept, what is the slope of the line of best fit? That's the 0.23. And the interpretation for this would be the predicted temperature goes up by about 2-3 degrees Fahrenheit for every increase in one chirp. So whatever the x or explanatory variable is, if you increase it by 1, that tells you how much the output variable, the y variable, response variable, goes up or down by. The intercept, which is 37.7, this would be the predicted temperature when crickets stop chirping, or when there are 0 chirps per minute. And there's big question marks here because that is the correct interpretation, but does that make any sense? I'm going to talk about later, like, oh, this intercept a lot of times doesn't make any sense in context. Mathematically it makes sense, but in context it might not make any sense. We'll come back to that. Okay, let's look at another example. The regression line to predict grade G, so here's my G hat, on the final based on the number of hours studying H. So H is the hours of studying. This is given to be 50 plus 3H. If one person studied 10 hours and received an 88 on the final, what would be the predicted grade for this person? Notice here, this 88 is the observed, the actual grade, but what would be the predicted grade? All right, I hope you've got 80. Go back 80. Because if you were to plug 10 hours in here, you have 3 times 10 is 30, plus 50 to get predicted grade of 80. All right, same regression line with the same variables. And if one person studied 10 hours and received an 88 on the final, what is the residual? In this one, you would take observed minus predicted. So that would be the observed is 88, and minus the predicted from the last slide is 80. Difference is 8. So residual of 8 for this student. All right, we take the same regression line with the same variables. How do we interpret the slope in context? Is it the predicted grade will go up by 1 point for a person who studies 3 more hours. The predicted grade will go up by 3 points for a person who studies 1 more hour. 3 more hours of studying gives 3 more points on the final. The rise of the run is 3/1. And the response variable goes up by 1. The explanatory variable goes up by 3. The best interpretation is going to be B. So the slope is 3 right here. So if we increase H by 1, that's if someone studies 1 more hour, they would predict that their final exam score would go up by 3 points. So A is wrong because the 3 and the 1 are switched. B is wrong because it's not interpreting slope correctly. 1 more hour studying gives 3 more points. D is also correct. The rise of a run is 3/1. If you think about the slope, that is the definition of the slope, but I'm going to be focusing more on interpreting. How do you interpret what the slope means? Even though D is correct, B is the better interpretation. And E would be correct if you switch the 3 and the 1. The 3 and the 1 are switched. If the response variable goes up by 1, if the response variable goes up by 1, the explanatory goes up by 3. The variables here are switched on E. So A, C, and E are all incorrect. D is correct, but it's not a correct interpretation. And B is correct and is a good interpretation of the slope. All right, now let's look at the same line of best fit, same variables. How do we interpret the intercept? Is it A, if a person does not study at all? The predicted grade will be 50. A predicted grade of 0 goes with studying 50 hours. The more someone studies, the higher the predicted grade. The line crosses the axis at 50. The response variable is 50 if the explanatory variable is 0. All right, now I want to go through this list and see which of these are accurate. But first, a good interpretation for this is A. Think about if H is 0, that would mean someone doesn't study at all. Then you just have 50. The predicted grade will be a 50 in the final exam. Okay, what about B? Predicted grade of 0 goes with studying 50 hours. B is incorrect. The variables are switched here. The more someone studies, the higher the predicted grade. C is accurate. This is a true statement because there's a positive slope. But again, it's not the correct interpretation, even though it's accurate. The line crosses the axis at 50 for part D. The line crosses the axis at 50. This might be true, but if we're looking at a scatter plot, there are 2 axes. So the line crosses the y-axis at 50 would be correct. But it's not clear whether it's talking about the y, the vertical axis, or the horizontal axis. And the response variable is 50 if the explanatory variable is 0. E is correct. This is correct, but not a good interpretation of what the variables mean. So again, A is correct, C is correct, and E is correct. All true statements, but C and E are not good interpretations, and B and D are both completely incorrect. Okay, so I want to go over some cautions with regression, and hopefully these cautions, these issues with regression lines and regression predictions will be hammered home after we do after you guys do the activity in the next class. But you do not want to use the regression equation or line to predict outside the range of x values. So if you have a bunch of data, if you go outside the range of the x values, that's called extrapolation. And you can get some really ridiculous results. That means if none of the x values are near 0, if all the x values are positive, then the intercept is meaningless in context. Again, it's a good mathematical value, but it would be meaningless because these 2 points go together because you're extrapolating. You're going far away from your known data. Okay, so I think it's helpful to think about units when you're interpreting a regression equation. The output's going to be the units of the y-axis, whatever they may be. The y-intercept, this is also going to be y units. The x, of course, is going to be the units on the horizontal axis, or the x units. And b is the slope. If you're thinking rise over run, the units will be the y units over the x units. So if we take an example where the temperature in cricket chirps, the y-axis is given in degrees. So that means the y-intercept, this is also degrees. This, the x units are chirps per minute. So here the slope is going to be the y units divided by the x units, or it's going to be degrees per chirps per minute. So degrees per chirps per minute. All right, let's look at an example here where we have, this would be weight. The predicted weight is equal to minus 260.4 plus 6.02 times height. All right, so what would be correct interpretation? The average subject is just over 6 feet tall. For every extra 6.02 inches in height, the predicted weight goes up by 1 pound. The predicted weight increases by 6.02 pounds for every additional inch in height. Or a 0-inch tall person is predicted to weigh about minus 260.4 pounds. It's right here. The predicted weight will increase by 6.02 pounds for every additional inch in height. Assuming those heights are in inches, you increase by your height 1 unit. That's going to be the increase in the weight in the output of the response variable. So before we go on, part D right here, this is the correct interpretation for the y-intercept. A 0-inch tall person is predicted to weigh about negative 260.4 pounds. That's the correct way to interpret the y-intercept mathematically. But I would say it's not a correct interpretation because this makes absolutely no sense. You can't have a 0-inch tall person or have negative weight. So this right here is an example of extrapolation. I don't know what data we know, but we definitely don't have any data for 0-inch tall people.